Hello everyone, welcome to my PhD defense. Thank you for coming. Today I'm going to talk about 5 of the projects I did towards machine learning for spectroscopic data analysis. But first I'm going to talk about some motivation for what I'm doing. This all started back at a company I collaborated with called MindSense. They make sensors for the mining industry. You can see a photo of me in front of one of their front-end loaders. The task here is we want to scan a rock or a shovel full of rocks and assess the value of those rocks. In particular, how much copper, how much gold, all the elements we're interested in, we want to be able to quantify the amount of those elements. And the task is to take the sensor data and build a prediction model going from a spectrum into element concentrations. And so my thesis is all about evaluating different models for doing this and comparing them, and then assessing which model to use for which elements. Essentially, we want to be able to map model into element. And in particular, we're interested in the neural network models because these have risen in popularity and in accuracy over the last several years. And so we're going to see how far we can push these models given the challenges of this particular application. The first challenge being the non-standard environment. So we have a messy non-lab environment where rocks are moving and turning, then there's dust in the air, there's snow in the air, and so we can't depend on the things we would normally be able to depend on in the lab. The second challenge is a lack of data. So any regression model, you need to feed it data. So this looks like a list of spectra. We also need labels corresponding to each spectrum, which are the element concentrations for every sample. These are much more expensive to obtain than the spectra, the sensor readings, because we have to send the rocks to a third-party assay lab where they're crushed into powder and then chemically dissolved, which is expensive to do, and it destroys the rock in the process. And so for this reason, we only have 177 labeled samples out of the 500 rock samples that we have in this data set. And so this puts us into the small data regime of problems. This is very much unlike the big data applications we've seen lately, like ChatGPT, which is trained on 300 billion words. That's a very different problem than the small data problems like this one. But these small data problems are very common in real-world applications, and so it's an important problem to look at. So I'm going to talk about 5 different projects corresponding to each of the chapters for my thesis, starting with the models that incorporate domain knowledge and then moving over towards models that learn from data. But in all of these models do both of these things. It's just that there's this spectrum of models and this in-between area where you can learn from data and from domain knowledge in the same model is not a very well explored area. And so many of my models are in this in-between spot. Now, the first way to deal with limited labeled data is through the use of domain knowledge. We spoke to domain experts and got the most important details describing an XRF spectrum, like this one, namely how the peaks relate to the elements. Each element produces a peak at a particular energy with some probability. I've labeled some of them here. And so I put all this into a database, and along with some other, with several other factors of how these peaks are generated in an XRF spectrum, I built this model that simulates a spectrum given an element concentration as input. So there's a diagram there, and there's a little animation showing different outputs of the simulator given different inputs. Now, there are existing XRF simulators on the market, but typically these require instrument and environment parameters to be specified, which are hard to obtain in a mining shovel. So I approximate these effects with parameterized functions whose parameters I then fit to the data. And the resulting model I call FitSim. This fits simulator parameters to an observed spectrum using gradient descent, particularly the ADAM algorithm. Here's a little video. So in this video, we're trying to fit the blue spectrum. The output of the simulator is in red, and that yellow line is an approximation to the instrument and the environment. And so that's just that weighs the output of the spectrum by the amount of that. So a weight of 1 is the top there. It's not on the y-axis. And so I'm going to play the video. You'll see that at first it fits the tallest peaks, those are the iron and copper peaks, and then the background continuum, and then several other elements, and then the weight parameters, and then more elements, and then the calibration parameters. And so these are happening in phases. And so I designed this to fit certain parameters in each phase, which is a manual process that I came up with for this data set. The end result is that it fits very nicely, but the downside is we have to do this manual tuning for every new data set. It also requires a good initial guess of the parameters, but the advantage of this method is that the fitting procedure itself requires no label data. We're just fitting a spectrum to the simulator. The only time we need the labeled samples is when we want to go from the parameter values into element concentrations. And so there we'll do a standard regression model, and you'll need a few labeled samples for that. But otherwise, it's an unsupervised model. That was the first chapter. That simulator I talked about, I'm going to use in 2 different ways. So I used it in FitSim, but I'm also going to use it in the next chapter in AutoSim. This is a model that incorporates the domain knowledge in the simulator, but also learns from the data. So it's a hybrid model that takes the best of both worlds. This is work that was published in the Journal of X-ray Spectrometry, and I also presented it at a workshop at NeurIPS. So first, I developed a convolutional neural network for X-ray fluorescence to use as a baseline with which to compare my model. And I also am going to use this later as well. So just a quick explanation, this is a convolutional neural network. It has the convolutional layer, which passes a filter over the input. Those filter weights are learned such that it extracts useful features from the input data. This is useful for pulling out repeated patterns in the input. So in this case, it's probably going to find peaks, but it might find edges or double peaks or other things that may repeat throughout the spectrum. After the convolutional layer, it's passed through a sigmoid function. This is to learn nonlinear relationships in the data and linear ones. These are followed by 2 fully connected layers, each with sigmoid activation and dropout, and then passing it. And then that's the output of that is the element composition. This type of model is used in many spectroscopy types, but at the time that I published this, there was no other convolutional neural networks for XRF. This is a supervised model, and so you need to pass it labeled data. That's the 177 labeled samples that I talked about. But we also have about 300 samples of the 500, which we have the spectra for those samples, but no labels. And so wouldn't it be nice if we could use those unlabeled samples as well? Hence the next model, AutoSim. So here, this is a neural network from a family of models called autoencoders, where the goal is to reconstruct the input at the output. And so it does this by minimizing the mean squared error between the input and output. And in doing so, it compresses that input data into a lower dimensional encoding in the middle, which is then decoded into a spectrum. This doesn't require any labels. You only need the spectra data. So that's very nice if you have limited label data. There's two parts to this, an encoder function and a decoder function. The encoder I replaced with the convolutional neural network from the previous slide. The decoder I replaced with the simulator from the first project. So there's a number of benefits. First one is that this learns how to invert that simulator so that we can, instead of passing in elements and getting out a spectrum, you could pass in a spectrum and get out elements. Another advantage here is that this outputs all 48 elements simultaneously in one model. Because the simulator has this built-in domain knowledge, there's not a lot of parameters that you have to learn. There's a few global parameters from that functional approximation I did, but otherwise that's a deterministic model. So compared to other neural networks, this has much fewer parameters to train. It constrains that encoding to correspond to element amounts because the input to this simulator forces those to correspond to elements, which then forces the encoder to learn how to output those elements. And so that's good. And the whole thing is unsupervised. You only need to give it spectra. You don't need any labels for this portion of the training. Now we also want to learn from the labels, and so we have another module, an output module that takes those element parameters and maps it through a fully connected layer to element concentrations. This is so that we can learn the concentrations of elements that are not visible to the spectrum, like lithium, which XRF can't directly measure, and so this module will learn the correlations between lithium and the other elements. And if you combine both the supervised and the unsupervised, you get a semi-supervised model. Here's some results after training it. You can see the output of the simulator in red and a couple observed spectra in black. It fits pretty nicely, except in the lower energy regions where they don't quite line up to some of these peaks. Here the physics are more complicated, so it's not entirely surprising that it's not fitting well. And the simulator that I built doesn't have all the physics, the nuanced details of the world. It just has the critical things for the majority of peaks, and so it's not surprising that it does poorly there. So then the next model I'm going to talk about is an extension to this autoencoder idea, but I'm going to make the decoder more general. So this model I call Spectra AE, and this looks at the problem of what do you do when you don't have a simulator. This comes up in other spectroscopy fields where the physics are more complicated, or maybe a simulator does exist, but it isn't differentiable, so we can't just throw it into a neural network. Essentially, my solution is to have a neural network learn to simulate spectra automatically by feeding it data. How do I do this? Once again, it's based on an autoencoder style architecture. And again, the encoder is replaced with a convolutional neural net, a slightly bigger one with different size features. The decoder is replaced with another convolutional neural network, but this time it's specially developed to generate spectra. So this has 4 rows of layers here in parallel. I'll explain the top one. We could do a fully connected layer from the element amounts to a vector of 1024. That learns to put in a high weight wherever there should be a peak for each of the elements. So if the copper amount is high, it'll learn where the primary peak of copper is and where the secondary peak of copper is, and just put in a spike in those locations. That gets passed to the convolutional layer, which learns what shape should be placed at each of those spikes, producing a spectrum. Each of the rows here does wider and wider features, so that we can learn to do the wide overarching background continuum, for instance. And once we learn all these different features, we stack them up by summing to produce the final spectrum. Here's the result after fitting it. Again, the red is the output of the decoder, the same blue is the input. the peaks are fitting very nicely. We can see that even the lower energy regions are fitting perfectly, and the rest of the peaks as well. So that's very nice. Now, I tested the performance of several models. Spectra AE is the one I just talked about. Lasso is a linear regression model, but with an L1 regularizer. PLS is a regression model designed specifically to handle multicollinearity, which is when many input variables are correlated to each other, and that's what tends to happen with spectra. It works in a similar fashion to principal component analysis, but with an added constraint that it must also correlate to your target element that you want to predict. FitSim is the model I first talked about. That's the gradient descent on the simulator. CNN1 and 2 are variants of the convolutional neural network. And so I compared all these models with 10 repeats of 10-fold cross-validation. That gives us a distribution of scores for each model. Then I used a statistical test, the paired t-test, to compare the distributions for every pair of models. And so, for example, here are some results. The green arrow means that the difference between those distribution of scores is statistically significant. And so we see a statistically significant difference between Spectra AE and PLS on the lithium prediction task. For zirconium, we see that it beat 3 models. The rest of them, that little squiggly equal sign means that the difference in distributions was not statistically significant, meaning that we couldn't assess one way or the other which model is better. We could think of them as being approximately equal, but statistically speaking, we don't have evidence either way. And so then to summarize these results, so this was just 2 elements that I'm showing here. We want to do this on all 48 elements. So I counted up the number of times each model beat the other models, and then in order to assess a winning model for each element. And with that, we can then build this nice map of the periodic table. The highlighted elements are the ones that were part of the prediction task. Those are the ones we have ground truth for. And then I labeled each element with the best performing model, or if there was a tie, then I listed all of the ones that tied. And so this is useful for, say, a mine that wants to know, okay, which model should we use for this particular element that we're mining. And so they might, for instance, choose to look at lithium, magnesium, and so on. Like these 4 are the ones that this particular mine that's their top 4 elements they might be interested in. We can also summarize the results by counting up the number of times each model won. So here I'm showing that Spectra AE is the best one on one element, but it was tied for best on many others. Now, both AutoSim and Spectra AE have some nice benefits. For instance, they can do outlier detection by taking a look at the reconstructions that they produce. If your reconstruction is poor, then chances are your model hasn't seen this type of spectrum before, and therefore its prediction may be inaccurate. It can also generate synthetic data, so you can generate data to train other models or pre-train a massive model and then fine-tune it on new problems. So there's some really cool extensions to this that could be explored further. Now, I will also point out that the Spectra AE decoder is general. It can apply to any type of spectroscopy. The results I showed was only on XRF. And so here I'm showing some reconstructions after training on all 3 types of spectra in one model simultaneously. And so it's showing that this is a good proof of concept. Now at this point, I was tuning hyperparameters of the model by hand or by grid search, which was tedious and difficult. And so I put this on hold to go address this problem of hyperparameter tuning for neural networks. And so that's what the next chapter is about. And this is something I published in the Journal of Chemometrics and Intelligent Laboratory Systems. here, the paper I did covers a bunch of problems. I'm only going to talk about one piece of it today, and that's the hyperparameter optimization. Neural networks have many hyperparameters, such as the number of layers, and rather than tuning these by hand or by brute force searching, I turned to the state of the art for this task, which is Bayesian optimization. Once I started using it, though, it was clear that it wasn't working. It wasn't getting a good configuration. So I needed to do an experiment with a known baseline with which to compare. And for that, I turned to this published data set of near-infrared spectra on 11,000 mangoes. And here they've published their code, their model, their hyperparameters, and their data. And so I was able to take their convolutional neural network, which they tuned and provided their hyperparameters. And they're experts in the field, so we can be fairly confident that this is going to be one of the best models you could come up with for this data. And so the question was, can I use the Bayesian optimizer to rediscover the hyperparameter configuration that they came up with automatically? We want to be able to automate away the expert. But there was another problem. I tried the standard automatic hyperparameter optimization technique, but it was unable to get anywhere close to the expert's model. This is because when we train a neural network, we get a different set of weights every time, which means the prediction accuracy is different every time. And that's an issue when we're trying to assess how good a particular hyperparameter configuration is. And thus it throws off the optimizer and we can't find a good configuration. So my solution is to use a known variance reduction technique called ensemble averaging. This is where we train several models with different random initializations and then average their predictions together. And so I did an experiment comparing hyperparameter optimization with and without ensembling. And here are some of the results. These are showing 2,000 trials of each of the experiments, showing the validation set error on the x-axis. That's what we're optimizing. And then I've also got the test set error on the y-axis. This is just our research purposes to see if it's actually working, but the model doesn't get to see this information. And so really what we want to do is minimize test set error, but we want to do it based solely on the validation error. So what this is telling us, that blue cloud is without ensembling. You can see that the cloud is very wide, meaning that there's a lot of variance, and it's unable to then minimize properly because it's got too much noise in the measurement of accuracy. But with ensembling, it tightens right up, and therefore minimizing using those red points is going to be more accurate than using the blue points. And we can see also the prediction scores on the test set of the final models chosen compared to that expert that we're trying to reproduce. So here, the expert model is in green. When we do regular hyperparameter optimization, we get the top blue box plot. But when we use ensembling, it drops down to a distribution of scores that is roughly on par with the expert models. And so we can celebrate and say, we've done it. And then I use this framework for the next project on sensor fusion, which is the final project I'm going to talk about. So here I'm going to employ the framework I just developed and the CNN model from earlier, put them together, and we're going back to rocks for this project. We're going to combine spectra from 3 different spectrometers on the same set of rocks and build one model to exploit the complementary information across the 3 sensor types. There are different categories of sensor fusion models. So in this study, I compared models from each of them. Low-level fusion is when you take all the spectra, combine them together into one vector, pass it through a linear regression model as usual. In high-level fusion, We learn independent models for each sensor and then take the predictions and combine them with another linear model that produces the final prediction. In mid-level fusion, you actually have one model that does the whole end-to-end task, but it knows about the different sensors, and so you extract intermediate features from each sensor and then combine those together all in one model. For that, I built a neural network specifically for that task. So that's the one I'm going to talk about. It starts off with a convolutional neural network, similar to the ones I used before for XRF, but then I repeat that similar structure for each of the three sensors, and then with those intermediate features, I just combine them with a fully connected layer to the final prediction. I tested these two elements. I'm only going to talk about one of them for the sake of time. This is showing the prediction error on zirconium. On the test set, which in this case was chosen by the duplex algorithm, the model listed at the top is our baseline, naive baseline model, which just predicts the average concentration. So this is the worst score that we could expect a model to produce. On the left are listed all the other models they tested. These are grouped by sensor, so the first three are XRF models, and then hyperspectral, which are the visible to shortwave infrared sensor, and laser-induced breakdown spectroscopy, or LIBS for short, and then the 5 sensor fusion models. The XRF models, they did very well, as expected, because zirconium is well within the range of XRF. Hyperspectral models did very poorly, also kind of as expected, because zirconium doesn't have spectral features in the spectrum, although the one model there, the PLS model, actually did get a bit of a signal, so it's doing a bit better than predicting the average, but poor overall. The LIBS models are somewhere in between. Zirconium is within the range of the LIBS sensor, and so we did expect it to exploit that, but the laser has a small surface area, and so it may not be as representative, which could be why it's not quite doing as well as XRF in this case, but reasonable performance. Here we can see that the PLS model and the neural network models, they're both doing on par with each other there. For sensor fusion now, I compared sensor fusion models from low level and high level and mid level. The best one overall was the high level PLS model that's combining independent PLS models from each of the three sensors. The second best was the high level neural network model, and so we can see that it's able to exploit different information from different sensors, so that's good. We can dig into it more by looking at the weights of the high level model. Here we can see that it put a high weight on XRF and almost zero weight on hyperspectral, meaning it's not even looking at the hyperspectral data. We could do just as well with just XRF and LIBS. So that's an interesting interpretability aspect of these high level models, which is nice. And so to conclude, the first model I presented incorporated domain knowledge of physics and geology, and then subsequent models relied more and more on learning from data. All of them dealt with the small data scenarios with limited labeled data and with a large number of features that spectra have. My contributions were interdisciplinary, spanning X-ray spectroscopy, chemometrics, spectroscopy, machine learning, and AI. And I reported the best model per element on a variety of models and tasks, including novel solutions for jointly learning from both domain knowledge and data. Since these small data scenarios are common in industry applications, the work in this thesis makes important steps towards this difficult problem. Thank you.